So in this section, we're going to talk about the 1990s all the way up to modern day. And I'm going to go ahead and talk about the future as well. In 1989, Sir Tim Berners-Lee was working at CERN, and CERN had an issue with their documentation. What I want you to do is think about this. Think about all the documents that are within a large company and put those all into one great big book. And this is the proposal that he wrote and was identifying the problem. So it's a thought process. So if we put all the documents in this one book, and any time a document needs to be edited, changed, or deleted, the entire book would have to be re-indexed. If you needed to add a page somewhere in the middle, the entire book would have to be re-indexed again. It's not an efficient system. And what ends up happening is it's very prone to errors and lost documentation. How are you going to find all of those documents? And that was the problem that CERN was having. So in 1989, he wrote a proposal. He came up with a distributed documentation system, a document information management system, distributed. Distributed means it doesn't matter where the documents are at. If we're using technology and we come up with the right standards and specifications, we can go and find all the documents that we need by using unique identifications. We don't need this large book trying to keep all this reference materials. So what he came up with was the World Wide Web. That in itself is a distributed system. So I want you to stop right there and think about this. Put yourself in a very large company. They do a lot of research. They have a big lab, and there's a lot of documentation that gets generated. How are you going to manage those documents? Think about that. How are you going to handle managing documentation? Yes, you can put them into a database and you can index things off of your database. And then you have version control. How are you going to handle all the version control? Without the web, it becomes very difficult. With the web, we're able to share information globally. It doesn't matter if you're sitting on one end of the world and the documents are on the other end of the world. You're able to get access to those because of the invention and this one proposal that he put together. Now, this proposal gave us the web, the distributed information system. He gave us the protocol, which we're going to talk about here, and how machines communicate with one another. He gave us the way to identify the documents so we don't have to re-index everything in that great big book every time something changes. And he also gave us the way to read these documents, a standard way. What he gave us were standards and specifications. He defined the entire architecture of this distributed global information system. So we're going to break this down piece by piece. Let's start with HTML. HTML is short for HyperText Markup Language. We're going to cover HTML in depth in another course. But for now, what I want you to know is that it specifies the formatting, the structure of web pages. It allows a piece of software sitting on a device, which is a browser, to be able to look at any document out there in the internet, out there in this global system, and be able to read it. Try to imagine in your mind. So here's a thought experiment for you. Imagine if we didn't have a standard, one unified standard, and everybody was putting information together out there on the internet. How could you read it? How would you be able to say that if John, this is a fictional person, John has his own format and this company has its own format and that one has its own format, how could we all read and share information across this system? We couldn't. It would be very difficult to manage a process like that, and that's where you get into proprietary type systems. But with this system, it's a global standard formatting structure that says this is how you lay out web pages. This is how a browser is going to be able to read that web page and present it to the viewer. So he also gave us a text-only browser, a way to be able to read those pages. to prove that, hey, I have this markup, here's my web page, and here's a browser so that I'm able to read it. Okay, so now I have a markup. I have documents sitting out there. I have a way to read them. How do I go get them? How do I find them? So I'm sitting here in my little house, and a web server is somewhere in the world. How can I go and get that document off of that server? I want you to picture in your mind the vastness and all of the servers and all the equipment on the superhighway that we call the internet. So when you open up your browser and you make a request for a document, it's got a path that it has to travel. It doesn't know that I go from point A to point B. Instead, it's got a lot of stops along the way to try to figure out, how do I handle the processing to send this information along? And that's part of the standard that he put together as well. But how do I find, I'm sitting at point A, I got to get to point B. Well, imagine if you had a system that didn't have a unique address. Imagine if you had a system that just said, my document, my addressing system might be the same as somebody else's addressing system. How could we find our documents? We'd have to write proprietary systems to then go and search specifically for those. But still, how can all of the nodes along the highway handle the processing to point it to the right place? It wouldn't work. We need a standard. We need a way to address and identify each piece of resource. And that's what he came up with. He came up with URI. We call it URL a lot, but it's actually URI. It's a uniform resource identifier. Now let's break this down. Uniform. That means it's a standard. We're all going to use the same structure. Resource, web pages, documents, those are resources out there that we're trying to pull into this information management system. Identifier, that's an address. That's a unique identification and addressing scheme. It's going to help us find documents and resources. So I want you to think about the address on your home, where you're sitting at right now. Think about that address. So if you were to tell someone, I live at XYZ Street, in this town, in this province or region or state, in this country, someone could be able to mail you a package or come to your home. You have a unique identifier on your home where you live. That is the same for these documents. No two have the exact same address, because if they did, could you imagine? Imagine if my website had the same address as your website, and now a viewer's trying to find it. They land on the wrong one. Which one is the right address? This gives us that uniqueness that we need to be able to properly access information. The next thing that we need, so we have an address, we have a markup, we know how to read documents. Now, how do we go get them? I just told you that there's a lot of nodes out there on the superhighway. So how is that process? How is that handled? So when I send a request out of my browser, how does it find where it needs to go to be able to find that web server somewhere else in the world? There has to be a communication standard, a protocol in place that says each machine, this is the packet of information you're going to get, kind of like the address on your package going to your home. It has a standard way of being presented so that each server and each node along the way knows how to handle and transfer that request along the path. So we came up with a standard way for machines to handle the request. Again, it's HyperText, that's what we're dealing with, transfer protocol, HTTP. Does that make sense to you? Break that down. We have HyperText, we have transfer, so it's a communication. How do we transfer the request from node to node to node? And the protocol is the standard, HTTP. So during this period of time, all the way up to modern day, we've seen a lot of different languages come into play that allow us to do our work. to be able to pick the right language for the right type of problem that we're solving. We also saw that computers are doubling in power every 18 months. That's Moore's law. That's been true for as long as he proposed that. So every 18 months, the computer is doubling in power. Think about that. So in 5 years, how powerful is a computer going to be? Look how small they are now. Now imagine in 5 years, 10 years, 20, 50 years down the road. Imagine the software systems that we'll be able to put in place for those. And we're going to talk about that here in a minute. Here's some high-level languages that have come along during this period of time. We have PHP, we have Python, Ruby, C#, and many others. These give us the tools, the specific languages that we can select for solving particular problems. They also allow us to focus on the business logic. So they're high level. We don't have to be spending our time trying to load memory up and dealing with all the nuances down at the machine level. They're high level. Of course, we have the internet. And applications are really becoming very popular. Mobile devices. Our world right now is very driven by being mobile. So what's the future going to look like? Well, we just talked about that the computer is doubling in power every 18 months. So I really want you to wrap your mind around, if the computers are doubling, that means we're going to have to get smarter and smarter about how we're processing software to push that computer to its limits, because that's what our job is. We need to maximize the web technologies, which includes the computers. So a web server is a computer. The computer you're looking at this device on, whether it's your mobile phone, an iPad, some other tablet, or the computer desktop or laptop sitting on your desk, those are all computers. So being able to be proficient in software, knowing your role in this industry, is going to help us to be able to prepare for when these computers keep doubling. It's what we've seen throughout this entire process as you're watching our industry evolve, is that the computers were starting to outpace us. So we had to get smarter and smarter about working more efficiently and putting systems in place that we could be more efficient and effective so that we are not the bottleneck. So we see that our role as a software professional is going to continue to evolve throughout the future, and you can be a big part of that. Our job is going to continue to be solving complex problems and pushing the computer to do more. Software is future-proof. We've seen that through the years. It's future-proof. Our world is very digital. It is driven by software and computers. So I hope that you've seen through this entire series the evolution of our industry and computers to help you understand your role not only in the past, but now and into the future.